Okay, let's take a look at this example. They're telling us that there's a car going around a road. Basically, a car is taking a curve and has a speed of v, or velocity, equals 2 times s, or 2 times theta. Let's look at, I'm going to call it theta now, where s is in meters. Okay, so actually no, it's not theta. Is let's say a length. This is an arc. Okay, this distance is an arc, right? It has units of meters. So obviously velocity has units of meters per second, and the arc or length has units of meters. Let's see, velocity is 2 times, so this is in meters. Interesting. Okay, so there's a little discrepancy in the way they present the problem, because if s has units of meters, then this constant has units of radians per second. All right, but regardless, let's just go ahead and follow this example. And then the curvature, the radius of the curvature is 50 meters. Okay, so this is actually used in civil engineering a lot to design the slope of this curve. Like if you watch a race, you'll see that these curves have a slope, so that they allow the car to take the curve without flying away. All right, so find the magnitude of the acceleration at 10 meters, or when L equals 10. So acceleration when L equals 10 meters. All right, so first we're going to calculate the velocity in order to calculate the acceleration, and then we have to calculate the tangential and the normal components. Remember the acceleration, when they ask you for the acceleration in curvilinear coordinates, polar cylindrical, then the magnitude of the acceleration is the normal acceleration squared plus the tangential acceleration squared. Okay, so let's look at the solution. All right, so we know the velocity vector is the instantaneous velocity times the unit vector in the tangential direction, right? That's already given. So since the magnitude is given, since the velocity is given by a function, so the velocity v is equal to 2 times L, then obviously when s equals 10, then it's obviously, so v when L equals 10 is equal to 2 times 10 equals 20 meters per second. All right, that's pretty easy. So they're telling us when s equals 10, what is the velocity? Is 2 times 10, 20. Very easy. That's easy to follow. Now, the problem is that they're telling us to compute the acceleration. And we know that the acceleration equation, A, is equal to A tangential, the form to express the acceleration. The magnitude is given like so, with normal in the square root of the components. But the acceleration vector, which is the question here, the acceleration vector is the acceleration tangentially with the unit vector in the tangent direction plus the normal component in the direction of the unit vector normally. This is the same as dv dt, unit vector tangentially plus v squared divided by rho, unit vector in the normal direction. If you notice, we don't have the v dt, and that's really the only complication in this problem. It's a matter of finding the dv dt term. Okay, so let's try solve over here. So A tangential is v dot, which is the vt. And again, don't confuse v dot with v prime. V prime is the v dx. This is with respect to direction. Okay, so don't confuse the v dot, the v dot with v prime. V prime is not the same because v prime is the v dx or the v dy, etc. V dot is the v dt. This is with respect to time. All right, so is the v dt, which is the term that we need to find. But in order to get the v dt from a function that is given us in terms of s or l, we have to do the famous chain rule. So dv, and we have to get to dt. So derive with respect to L and take the derivative of L with respect to t, or dv ds dt. So this guy right here is my velocity term. So is v times dv dl. Okay, or in their case is v dv ds. All right, so since we have this now, which this is equal to the tangential velocity, then what we can do is bring our term down here. So at, this is acceleration in tangent direction, is the change of 2 with respect to L dl times dv dt, and dv dt is my velocity term. All right, so in that case, we get the derivative of 2L with respect to L is 2, and well, this is just velocity. So my tangential acceleration is 2 times v. This case was very simple because it's just L. Could be complicated when you have a weird function, L to the exponent or L to the square root, a square root of L, something like that, when you have to actually find the derivative using the chain rule. But this one was pretty easy, and that's good. So when tangent acceleration, when they're asking us when is 10. Okay, 10 is equal to our velocity, which is 20 meters per second. Let's see what's going on here. But we don't have time anymore, so we cannot go ahead and replace that just like this. What we do is that's why we do the chain rule, because this is 2 times the velocity. So 2 times, and what is the velocity? 20 meters per second. Okay, so 2 times 20 meters per second. And these two, remember, had units of 1/2. Okay, I know it's a little weird, but it's radians per second. So 2 radians times 20 is equals, radians are not going to affect the units here, is 40 meters per second squared. Okay, so in that case, which is what we got here, since our acceleration tangent is 40 meters per second squared, which again is 2 times v, but this v, this velocity v, was found up here. All right, that's good. So that was 20 meters per second. 2 times 20 is 40. So we have the tangential acceleration. Now to find the normal acceleration, which is pretty easy, is v squared divided by the radius of the curvature. So this is velocity is 20 squared divided by the radius, which was 50. Yes, 50. And remember, the velocity is 20, which is right here. 20 meters per second. It's not 40 because this is the acceleration. It's v squared is 20 squared divided by 50. And that is 8 meters per second squared. Right, 20 squared is 400 divided by 58. So the total acceleration is equal to square root of 40 squared, because it's the tangential acceleration that we found is right here, plus 8 squared, square root of that, and that is 40.8 meters per second squared. And the vector, the way to write down the vector is acceleration equals to a term tangential plus or minus, depending on what we use, but in this case, what we get in this case is plus, is tangential is 40, and normal is 8. So that's the acceleration vector.